the end of last night, we talked about energy involved in phase changes. And I think that's important because phase change, sort of the chemistry behind phase changes pretty much has everything to do with how molecules interact with each other, because that's basically what's happening during a phase change. You're interrupting the pattern of molecules interacting with each other. Because we know in the solid phase, molecules are very close to each other, interacting very, very tightly, holding on to each other with a lot of force. Then you break those interactions to move it into the liquid phase, where the molecules are able to move more freely, but they're still interacting with each other. And then finally, you have to break all of those interactions in order to move the molecules into the gas phase. And each one of those takes energy. And as we've been learning, breaking bonds requires energy. Breaking bonds is an endothermic process. You need to add energy to get bonds to break. Forming bonds is an exothermic process. When you form bonds between different molecules or different atoms, when you form these sort of interactions, energy is released as more stability is achieved, and that's exothermic. And so we're going to look how we can put these things all together tonight, hopefully. So we talked yesterday about there's a certain amount of heat that's either required or released during a phase change. And it's different from the sort of the amount of, the way we've been looking at heat so far, is when we calculate Q, if you remember, let me get myself something to write with here. Your lab, both either this afternoon and tonight, was concerned with calculating Q. And so the expression we've been using to calculate Q, we're all sort of familiar with. We need to calculate Q, which is the amount of heat. We need the heat capacity. How much heat does it take to raise the temperature of that substance by 1 degree for every gram of it? Then we need to know the mass. And we need to know how much we're changing that temperature. Obviously, if we're changing that temperature by 50 degrees, that's going to take a whole lot more heat than changing it by 5. Now, that's different from when we're calculating phase change heats. Heats during when something's freezing or boiling or melting or subliming or whatever two phases it's moving in between. And so we learned that water has what we call a latent heat. Latent heat refers to the heat involved during a phase change. And the latent heat of fusion is the amount of heat that's involved between the solid phase and the liquid phase. So when we say it's fusing, obviously it's going from the solid to the liquid. But when it's melting, it's actually doing the same thing, but just in reverse. So we just reverse the sign. And in this instance, when we're calculating Q, and here's our calculation of Q for when something's freezing or melting. And you'll notice that it's different from the Q we've been using. What's different about it? What's different about this particular form of the calculation of Q and the one we've been using before? There's a difference in the expression.
CP?
Yep, that's one thing.
Yeah.
Yep, we don't have a heat capacity anymore. But in a way, the latent heat of fusion is basically takes the place of the specific heat. They're both a measure of how much energy is required per gram of a substance. So it's similar, but not exactly the same. Yeah, so that's one difference. There's another one.
There's no temperature?
There's no temperature. There's no, when we calculate Q in solution, we take into account the change in temperature. How come we don't do that during, when we're calculating the heat of fusion for either melting or freezing? How come we don't do that? Can you remember all the way to last night? Seems so long ago. We were so young back then. Young and full of hope.
Can you repeat your question again?
Why don't we consider the change in temperature when we're calculating heat of freezing or melting?
Because the temperature is the same.
That's right. Exactly. The temperature doesn't change. Melting occurs at 0 degrees. Freezing occurs at 0 degrees. The temperature doesn't change during the melting and freezing process. And if you remember from the melting freezing curve, the phase change curve we showed last night, and I'll show it again in a minute. During freezing or melting, the temperature didn't change. It stayed at 0. When was the other part of the phase change curve where the temperature didn't change? It didn't change at 0, and it didn't change at another temperature.
100.
Yeah, it didn't change at 100. So what's happening at 100?
Vaporization and condensation?
Exactly. Yeah, we're boiling the water. So the water is changing phase from the liquid to the solid, liquid to the gas, or it's condensing back from gas back to a liquid. That happens at 100 degrees. And so at 100 degrees, we're adding more and more heat. We're converting more and more liquid into gas, but the temperature stays exactly the same. So if we're going to calculate a whole bunch of different phase changes, we have to take these things into consideration. So when we're dealing just with heating, just with freezing or melting, we deal with this number, 334 joules per gram. That's how much energy you need to put in to get it to melt, or that is released when it freezes. And the same is true during the vaporization and condensation phase. We have also another latent heat, this time HVAP rather than HFuse for vaporization. And this time, if you remember, that the number was a lot bigger. It takes a lot more energy to get water out of the liquid phase into the gas phase than it does to melt an ice cube. It takes a lot more energy to take water into vapor than it does an ice cube into a liquid. And again, no change in temperature, stays at 100 degrees. So this was the energy, this was the phase change diagram we looked at yesterday. And so we saw that it was divided into a bunch of different phases, bunch of different sections. So A to B is just the increase. A to B is the increase in temperature of ice as you're melting it. So that is ice increasing in temperature from -25, which is at the bottom, to 0. But then once we get to 0, this is melting. So that's melting there. And then as we put even more heat, all the melting's taken place, and we have water liquid rather than water solid, all the way from C to D. And for that, how would we calculate the change in heat of just the liquid water? It's basically here we're looking at heat being added in the x-axis, and we're looking at temperature change in the y-axis. How would we calculate the amount of heat required to change that temperature when we have liquid water? So we use, get a different color. So we use H fusion for when it's freezing. And we use H vape, delta H vaporization, when it's boiling. What do we use in between? What do we use here when we just have liquid water? How do we calculate that? What equation are we going to use?
The one that incorporates the change in temperature.
And what one's that? We need 3 pieces of information to calculate that. What 3 pieces of information do we need to calculate that heat? Go on, Sabrina. I know you're dying to tell me. What is it?
Boiling point constant. I don't know.
Boiling point. Well, no, this is the boiling point constant, basically. The delta H vaporization.
Oh.
So that's basically what we use to calculate the amount of heat during the boiling process. But when we just have liquid water and we want to calculate the heat involved with a temperature change, how do we do that?
Don't we have to calculate Q?
Yeah, we do. That's exactly right. So what formula do we use for Q in that regard? Because Q over here, oh, go ahead.
Specific heat times mass times change in temperature.
Bingo, exactly. Right, so basically we have to calculate all of these changes. So Q for this phase, when H2O is a liquid, is our usual times delta heat capacity, mass, delta T. When we get to then that only works till we get up to 100 degrees. Once we get to 100 degrees, the temperature stays the same, but we're still adding heat. And that's when we use delta H vaporization, because that tells us how much heat is involved in boiling that much water. And the same is true for the ice. Now, we don't think of it that much, but down here, this part of the curve between A and B, that is just the same as for the liquid, because it's not a phase change. Everything is ice, but we're adding heat to it and it's changing temperature. And so for that, we'd have Q for the solid, Cp, times the mass of the ice, times the change in temperature of the ice. Now the question is, would we use the same specific heat?
No,
No. How come?
because the specific heat for solid water is 2.11.
Right, it's different. It's a different substance. It's water, yeah, but it's not the same substance. It's solid now. And so what we're dealing with is breaking the interactions between solid molecules in water molecules in a solid and converting them to water molecules in a liquid. That's different. It takes half as much energy, basically, to break these interactions in a solid and replace them with interactions in the liquid. Why? Because there's still a lot of intermolecular interaction when the water's in a liquid. You're not breaking them all. In fact, you're maintaining most of them. And so it's much easier to increase the temperature of ice than it is of water. And then look, when we get to water vapor, the specific heat is about the same as it is for as it is for ice, which shows you that it's relatively easy to break those. But you can see that even the specific heat of water vapor is greater than that for like metals and everything else. Metals still have a really low specific heat comparatively to water, even in the gas phase. So if we were to calculate something like this, we have to break down each one into different stages. So I was just going to take you through that because there may be a question on a test in your future. Not saying there is, just saying there might be. There might be a question like this. So, how much energy is required to boil 50 grams of ice that you take out of the freezer that was at minus 20? Generally, the temperature in your freezer is around minus 20 degrees C. So you take an ice cube out, big ice cube. It's 50 grams ice cube. Maybe it's one of those big clear ones that hipsters put in their drinks. And so you want to convert that to water vapor. How much energy is that going to take? So what would be the very first thing we would have to calculate? Because what are we starting with? We're starting with
Solid.
right. We're starting with H2O solid. And what are we doing with it? What's the very first step that's going to happen?
Heat it up.
Hit
We're
Q.
heating it from minus 20 to what temperature?
0.
Right. So we're going from, so to figure out this first step, this first stage is heating the ice to the melting point. And so that Q would be 2.11 joules per gram per degree C times 50 grams times 20 degrees, because we're going to go from minus 20 to 0. So that would be our first step. What would our second step be?
The energy to convert to liquid.
Man, you're on fire tonight. On fire tonight. Is that Aaron?
Yes.
Good job. Good job, Aaron. Yeah. So we're transitioning from a solid to the liquid. That's a phase change. And so when it's a phase change, we need to figure out which phase change it is. And it's fusion. And so now Q1 is the phase change. It's just getting us to the freezing point. Q2 is then just equal to 334 joules per gram times 50 grams. That one's pretty straightforward. So at this point, we've moved our ice to the freezing point, and now we've melted it all. So what's our third step?
Amount of energy to heat it up to boiling.
What phase of water do we have?
Liquid to
Liquid.
Just liquid. We just have liquid. We're not going to consider converting it to gas until we get to the boiling point. So right now we strictly have liquid. So our Q3 is going to be, now we have the specific heat of liquid water. So 4.18 joules per gram per degree C times 50 grams times, what's our change in temperature going to be?
100.
100. Yeah, because we need to go from the freezing point to the boiling point. We need to go to whatever the distance is to the next phase change. And with water, It happens to be 100, from 0 to 100. So that change is 100 degrees. Now, what's my fourth step?
Liquid to gas.
That's right. Man, you guys are sharp tonight. Did everyone eat before lecture? I'm starving, but yeah. Second phase change, liquid to a gas. So this time we're undergoing another phase change. So that will be independent of temperature because it's just going to stay at 100. And which phase change is it? All right, it's the phase change from a liquid to a gas. That's vaporization. So our Q4 is going to be 2,260 joules per gram times, again, our 50 grams. So to solve the problem, we would just add Q1 plus Q2 plus Q3 plus Q4. Add them all together. And that would be the total amount of energy required. Now, there would be a fifth step if the question said, and you wanted to heat the water vapor to, let's say, 300 degrees C or something like that. Then there would be the fifth step of just increasing the temperature of the vapor from 100 to 300 using the water vapor's specific heat. But that wasn't the question. You just needed to boil it. You just needed to turn it into vapor. And so you just add Q1, Q2, Q3, and Q4. Okay? So is everyone clear on that? Why we need the four different steps?
So if if the question was like what you just said, if it set the temperature to like heat the vapor up to a certain type, would there be a Q5 and a Q6?
Just 5. There's no Q6 because once we've got water into the vapor phase, that's it. We can't get it into any other phase higher than that. There's just basically there's just 4 phases. There's solid, liquid, gas, and plasma, and so we're not ionizing it, so we're not turning it into plasma. So we don't have to consider that. We're just keeping it a gas, and as a gas, we can heat it till it's almost pretty much infinitely hot, and that would just be taking into consideration the specific heat of the vapor. So it'd just be the mass of the gas, 50 grams, the specific heat of the water vapor, like 2, and then however much we're changing the temperature by. So it'd just be 5. You wouldn't have to include another one.
Okay.
Yeah. All right, cool. Just saying it might be on a test. Just saying. Not threatening anyone, just saying that might happen. Okay. So I'm going to start chapter 10. And we're not going to have any recitations. Next week, we're going to take our recitation time and our lab time to review for the test. And for the lectures, what I'm going to do is sort of go back to the very beginning and sort of hit the highlights of the chapters we've covered so far. And then the recitation in the lab and my office hours, we'll be answering specific questions that you guys have and working through them. Okay, so there may be a question or two from chapter 10, but I'm not going to assign any specific questions for you to do. All right, mostly it's for understanding of the chapter we just finished and sort of relating back to the chapter on molecular shapes. But I think it's one of my favorite chapters because I always say that. But because as a molecular biologist, as a biochemist myself, this is where the biology comes in. It's the interaction between molecules that really defines biology for me. And so hopefully you'll pick up on some of this as we go through, because there's, as I point out here in the slide, The molecular shapes of things have real world effects, and very important real world effects. And I'll try and explain some of them as we go along. So I'll just give a brief overview of the physical states of phase changes. You guys know this part, you know, all the way through. Quantitative aspects of phase changes, we've just been through that. And then talk about the types of intermolecular forces that are basically responsible for these phase changes. We talked about a couple of them in lab today, actually, because one of the things that you'll be doing in your lab is taking sodium hydroxide as a solid and putting it in water, and where it ionizes. Doesn't actually ionize, but it already was ionized. But the ions become free from each other. And we sort of briefly went over how what happens when you do that is that you're replacing an ionic bond here. That takes energy to do. It takes energy to break an ionic bond, because that's a fairly strong bond if you remember. But we also found out that when we dissolve sodium hydroxide in water, it's an exothermic process. It actually releases quite a lot of heat. And that was surprising because it takes energy to break that ionic bond. And so we found out from earlier, the work we've been doing, is that breaking bonds takes heat. That is an endothermic process. Forming bonds makes heat. It releases energy. It's an exothermic process. So what bonds are being formed? And so what we learned today is one type of the intermolecular force that's going on that's responsible for this. And we're going to talk about that. Anyone remember what bonds are being formed when we have sodium ion and chloride in the water? Do you remember what happened?
Ionic?
It was an ionic interaction. It was an ion. You remember what kind? It was a specific kind of interaction. It was an ion. It's an ion dipole interaction. So the ion is either the sodium plus or the chloride minus, and the dipole is water. Because we know this goes right back to our molecular shapes. Water is a dipole. It has a slightly negative side, which is the oxygen, has a slightly positive side, which is the hydrogen side. And so it's a slightly negative side that interacts with the positive ion, sodium, and it's a slightly positive side that interacts with the chloride ion. And so you replace that single ionic bond with a whole bunch of these ion dipole interactions. And the net, and that's what we're always looking at. We're looking at the net amount of energy at the end. Did it take more energy? Do you have more energy at the end of it, or you have less? Well, you have less energy at the end, because the energy you spent breaking the ionic bond, you get back and release when you form these ion dipole interactions with the ions in solution. That's why sodium hydroxide is really soluble in water. It also explains why some ionic substances are not soluble in water. Remember we talked, which ionic substances were not soluble in water? Do you remember what kinds they were?
Iodine?
Iodine is not, that's I2. That's not an ionic, that's a molecular compound. It's not ionic, it's covalent. There's a certain sort of group of ionic compounds that had something in common that just didn't dissolve.
Non-polar?
Well, if they're non-polar, they can't be ionic. You can't be both. If you're ionic, you're super duper polar. Can anyone think of like an ionic compound that wasn't particularly soluble that we talked about? I'll give you one. See if you recognize it. Calcium phosphate's really not soluble in water. How come? Remember you're like in your lab, you're like precipitating out arsenate compounds, and phosphate compounds weren't particularly soluble. Why is that? Sodium chloride is soluble as hell. You can dump tons of sodium chloride into water and it dissolves easily. But calcium phosphate, not so much.
It's because of their charges, right?
Yeah, it's because of the charges. It's because here we've got a +1 and a -1. And here we've got a +6 and a -6. So the ionic bond in calcium phosphate is extremely strong. And Jerome. And basically the water, interaction with water could not overcome that strong a bond. And so it just sinks to the bottom. Whereas sodium chloride with just +1, -1, there's enough interaction with water, it can break that and then replace the strength of that bond with all these ion dipole interactions. But calcium phosphate, not going to happen. Generally, anything with a really, really high density of charge is not going to be terribly soluble in water.
So group 2 and transition metals.
Not all of them. I mean, it depends on what they're, like calcium chloride is soluble because the chlorine's only -1. It's when you have like aluminum phosphate, when you have like, +3, -3.
Oh,
That
okay.
is like really, really, really strong. That's not going to break. Calcium chloride is not as soluble as sodium chloride, but it is somewhat soluble. Whereas, so basically, solubility isn't absolute. It's not like you say it's completely insoluble. Yeah, some of it's soluble, but very, very little. And then your solubility increases the less and less strength of that ionic interaction is.
Got it. Thank you.
No problem. So each physical state we just call a phase: solid phase, liquid phase, gas phase, and they're physically distinct. And we've seen that they have physically distinct properties, like their heating constant, their specific heat is different depending on what the phase is. And the properties of each phase, we sort of looked at the kinetic energy of the particles. The slower the particles move as it moves to a solid, and the faster they move, we go up to a gas. Now, the potential energy we haven't really talked about. That's what we're going to talk about now. We've only been talking about the kinetic energy, how fast the particles move. We also have potential energy in phases of matter. And the more potential energy you have, the more likely you are to be a lower energy state of phase of matter, solid, liquid. Gas has a very little potential energy because the potential energy is in the form of attractive forces, how molecules interact with each other. And the stronger they interact, makes sense, the more they're going to be close to each other. The closer they are together, the more that phase is going to be to the liquid or the solid. The less they interact with each other, it makes sense that they're going to be further apart from each other and more like very low density liquid or a gas. So that's potential energy, these attractive forces. That's what we're going to be talking about in this chapter. So kinetic energy tends to disperse particles apart, and potential energy draws them together. So they're basically opposite to each other. One wants to fly them in all directions, and the other wants to bring them apart and have them not move around so much. So these are some of the attractive forces we're going to be talking about. We're talking about intramolecular bonding. And I still, to this day, have trouble with getting these two. If you have trouble remembering what the difference between these two, you are not alone. Intra and inter. How many people, took part in when they were, sports in college? They were like intramurals. They're not intramurals, they're intramurals, because they're found within the college, not between. So people mix that up all the time, and I still mix it up. So intra is inside a molecule. And I find that confusing because inter should be internal, right? But it isn't, it's the opposite. I don't know why, I didn't make up these rules. So intramolecular are found within a molecule. They hold a molecule together. So the chemical behavior of each phase is the same because the particles are the same. So when we talk about the physical behavior of each phase of matter is different, but chemically they're all still the same thing because still water. That's one thing that like beginning chemistry students have a really hard time with, that when you boil water, it doesn't turn into hydrogen and oxygen. It's still water, it's still chemically linked. So its physical properties are different, but chemically it still reacts like water does. It's still gonna rust iron, regardless of whether it's ice, liquid, or a gas. It's still gonna do this, do the same chemistry. But intermolecular forces are non-bonding. They're not sharing electrons. So intra is the things that hold atoms together. Single bonds, double bonds, pi bonds, sigma bonds. Those are the things that hold atoms together inside a molecule. Intermolecular forces are different. They involve interactions between different molecules where electrons are not shared. So they don't form what we would call a formal chemical bond. But it is still an interaction that we can measure. And some of these interactions are very, very strong, as we'll see. And so these involve the physical behavior of all these types of matter. Because like I pointed out, water is water is water is water. Doesn't matter what phase it's in. But the interactions between those water molecules are different depending on whether it's ice or liquid or a gas. And so those are between molecules, intermolecular. So I'll be talking about intermolecular forces. I may say intra at some point. It's because I'm stupid and I can't keep remembering this. But maybe it's just because I keep convincing myself that I'm confused. But yeah, so this intermolecular is what we want to be talking about during this particular chapter. I don't mean that you won't be able to remember it. I just know that I can't remember it. So if we just look at the kinetics, and we've done this already, in a gas, hey, must we? In a gas, attractive forces are super, super weak. Because remember, one of the things we took to be true when we looked at the gas phase and doing all of the calculations for the gas laws, one of the assumptions we made that there was no attractive forces. Remember, we had to say that they had no volume and no attractive forces. Well, neither one of those things is true. They just have very little attractive forces, but a lot of kinetic energy. So that's why gas has no fixed shape. It doesn't have a fixed volume, because these attractive forces are so weak, they'll just fly out everywhere. Now, when you get to with liquid, you're starting to balance kinetic energy and attractive energy. Kinetic and potential energies are starting to balance out. So they're much, much stronger now because particles have less kinetic energy. They're not moving around quite as quickly. They have time to interact with each other. When they interact with each other, then we have attractive potential forces, potential energy. And that means that a liquid can flow. It doesn't like fly around. It can flow and it can change shape, but it has a volume. If I have 50 mils of water, I dump it on the floor, I still got 50 mils of water. It's not the same shape, but the volume stays constant. And then with a solid, attractions completely dominate kinetic. And that makes sense because, you know, your table or whatever is not flying around the room. It's staying in one place. Those attractive forces completely overcome the kinetic forces. Particles are fixed and they stay fixed relative to each other. So now we have a fixed volume and a fixed shape, okay? So now we could look at some of the other physical properties of these three things. So with a gas, we all know, I've sort of been saying it from the beginning, a canister of gas is always full and it's always empty. And what the hell does that mean? It means that whatever shape and size that gas canister in, no matter how much gas you put in, it's going to bounce around all the sides of the canister. It's not going to have a terribly high pressure, but it's going to be bouncing all over the place. So it's going to conform to the shape and the volume. Now, it's very compressible. I think we saw that, right? We can squeeze gases. And when we squeeze gases, the pressure goes up as the volume goes down. That's not true with liquids. Liquids are not very compressible at all. In fact, that's why hydraulics actually work on this principle. You can shoot water through tubes and have water, you know, a tube full of water, you know, pick up a car off of somebody because it's not compressible. If you put enough water pressure in there, you can basically move anything because it will not, you can't squish it. It's not compressible. It will conform to the shape of the container, but you can't compress it any more than it already is, but able to flow, obviously. And then a solid is basically not compressible at all. Although, as we mentioned with the, like, you know, the Golden Gate or the Bay Bridge, it's compressible slightly because, you know, that's why there's gaps in it, because it is going to, when it's warm, if it's ever warm, it will expand and fill in those gaps. And if those gaps aren't there, the concrete and the metal will buckle. And so you don't want that. Obviously, you don't want that to happen. So we looked at these phase changes and we looked at the enthalpies. So I'll just go through this rather quickly. So we've seen that gas phase comes back into a liquid, call that condensation. The opposite of that is vaporization. And so the enthalpy of condensation, you remember, is that going to be positive or negative? Is that going to be endothermic or exothermic? When I condense from a gas to a liquid. What's the sign of the enthalpy of that reaction? Is that going to be positive for endothermic or negative for exothermic? Am I losing energy or gaining energy? Or is it gaining energy or losing energy?
Losing energy?
It's losing energy, right? Yeah, it's going from a very rapid motion. There's a lot of kinetic energy, and it's losing that kinetic energy, and so it's becoming more stable. It's going to lose energy, that's going to be exothermic. Same is true from liquid to solid. We saw the difference freezing and melting, and then finally gas to solid and back and forth. And we know that dry ice is called dry ice because it isn't really have a liquid phase. You can get it into a liquid phase at very high pressure. In fact, canisters of CO2 are liquids inside because it's at an extremely high pressure, like 50, 60, 100 atmospheres of pressure. And under that kind of pressure, you can actually force CO2 to become a liquid. But at 1 atmosphere, it goes directly from solid to a gas. So we call that sublimation. And then the opposite would be deposition. So let us continue. So these are all the enthalpies we've talked about. Anything where you're moving sort of up the chain, you're increasing the kinetic energy of the molecules. That requires heat. Those phase changes are going to be endothermic with positive changes. Those are going to have positive changes in the amount of energy you need to put in. On the other side, when we're decreasing the kinetic energy of our molecules, gas to liquid, liquid to solid, those all release heat. And it seems weird. Whenever we think of like an exothermic process, we usually think of something, you put your hand on, it's going to get hot. Whereas a gas turning into a liquid, it's actually getting cooler. But it's a physical reaction, not a chemical reaction. And the molecules, after the fact, have less energy in them than they did before. That is an exothermic process, even if it doesn't feel that way. Energy is being lost. And so all of these are dropping in energy. And so we're going to call those negative. Okay, so I think everyone's probably pretty familiar with these, hopefully. We've sort of talked about them quite a bit. Now, something we have not discussed to this point is equilibrium. Can anyone tell me what equilibrium is? Or have you, if someone says equilibrium to you, what do you think of?
It should be equal.
What's that?
It should be equal.
Yeah, something is equal. That's true.
Endpoint.
Something is
Endpoint.
equal. It's and what?
Endpoint. Like when the reactant will be reach the product side.
When the reaction.
I mean, it's endpoint. The
an end point.
Yeah. Kind of.
Oh, I mean when a reaction's over.
It's different.
That is different.
Okay.
So the first things, when something's equal, does that mean that it's equal and unchanging? Is that what you think of? Like when two things are the same, do they have to be the same for an equilibrium to take place?
I mean, in the beginning they are different, but at some point they reach each other. They become equal.
So the two things have to be equal to achieve equilibrium.
Yeah.
Okay. Does everyone agree with that? Or anyone? Oh man,
But initially they are different. This is my point.
Yes, that's true. Initially things, at the beginning of a reaction that goes to equilibrium, things are different. But do they necessarily have to be the same? So like if I have,
Is it that the change between the two is not changing?
oh man, Aaron, you were crushing it tonight. Yes, that's exactly what I was going to say. If I have equilibrium between A and B, so basically that means my reaction is going both forward and backwards. It doesn't mean that the concentration of A is exactly the same as the concentration of B. What it means is that the concentration of A and B are no longer changing. So it could be that I have 90% A and only 10% B, but that's what their equilibrium values are. That's when I have a stable equilibrium, that is the values. And so I would say my equilibrium constant here is 9 divided by 1. So it would be 9 favoring A. They don't have to be exactly the same. And I actually studied a sort of form of equilibrium when I was in San Diego at the Scripps Institute. We studied a virus. This is an idea of a biological equilibrium. So we studied a virus called cytomegalovirus that some of you may or may not have heard of. It was found to be a problem during the AIDS crisis back in the 80s and 90s, was that people who had AIDS were getting these infections of cytomegalovirus, a lot of them in their eyes, and people were going blind. I don't know if you remember that. But people were wondering, well, where the hell is this virus coming from? Because pretty much all of you, and this is going to be shocking, have cytomegalovirus right now. And so about 75% of the population has cytomegalovirus, but it isn't a problem. It isn't a problem because it's expressed at extremely low levels. It basically is dormant. And that's what was thought for 10, 20, 30 years, ever since someone discovered it. It thought it was dormant, that it was dead, but it wasn't. It was in an equilibrium. And so what happens if you disturb the equilibrium, and with the case of HIV infection, the equilibrium was disturbed by taking out those T cells, the white blood cells that were keeping the cytomegalovirus in check. Once those were destroyed, you had a huge increase. And so it wasn't dormant. It was constantly being created and destroyed, and created and destroyed, and created and destroyed. And it was what's called a dynamic equilibrium. And a dynamic equilibrium is established when things are changing in both directions, but at the same rate, just like you said. They're changing at exactly the same rate. And so the vapor pressure is an example of that. The vapor pressure, it's just the pressure exerted by vapor on the liquid. So here we've got liquid, and when we have a vacuum, so we can just imagine this liquid could be anything. It could be water, it could be ethanol, it doesn't really matter what it is. You establish a vacuum in there. Some of that liquid is going to turn into the gas phase. And we saw that when we looked at the partial pressure. Remember, we were looking at the partial pressure of water, that when you were collecting gas in the presence of water, you had to take into consideration the pressure of the water vapor at different temperatures. Because even at 0 degrees, even when you have ice, a certain number of those water molecules are going to become vapor. Not very many, but some are. And so at some point, you're going to find an equilibrium between the amount of gas and the amount of liquid. And that means that the rate of vaporization from liquid to gas and the rate of condensation from gas to liquid are exactly the same. And when that takes place, you have an equilibrium. And then your pressure becomes constant. And that pressure is actually, that would be the partial pressure of that liquid at whatever temperature. So pressure would be different depending on what the temperature is. The higher the pressure, though the higher the temperature, the higher that equilibrium pressure is going to be, until you get to the boiling point. And then we see that the equilibrium is going to be all towards the gas. And then your vapor pressure is going to be equal to the atmospheric pressure, whatever it is. So everyone clear on the difference between a static equilibrium where things aren't changing, and a dynamic equilibrium where it looks like things aren't changing, but they're actually changing at the same rate in both directions. It's kind of important. You're going to be anyone going forward doing any sort of science is basically going to be seeing these two different equilibriums all the time. And most equilibriums are dynamic. Most things are changing back and forth. Okay. So we looked at the effect of temperature. We noticed that not every molecule moves at exactly the same speed at the same temperature. It's going to be a range. But as we move to higher and higher temperatures, we see that the distribution gets wider and wider and wider. We get more and more molecules. The average moves, but we get a bigger and bigger range. And then eventually we move the temperature so high that all of the molecules are now moving fast enough for them to completely change to vapor. And so when that happens, basically what has happened is that we have our kinetic energy, which wants to turn things into vapor, and we have our potential energy, which wants to have the molecules stick together. So what's happening out here, the kinetic energy has basically overcome the potential energy. It's now much greater, and it's kicked potential energy to the curb, and now all of the molecules are moving quickly. When we lower the temperature, we lower the kinetic energy and allow the potential energy basically to catch up. The potential energy is basically going to stay the same, and the kinetic energy is just going to get less and less and less and less and less until the potential energy is more, and then we go from gas to liquid to solid. Okay? Let's get into some of these. So, some of the things affecting the pressure of vapors. So as temperature increases, they're moving faster, we're going to have a higher pressure. Figured that out. I mean, that's what we've been dealing with in the gas phase. All of our calculations have showed that. You showed that in your labs. When you change the temperature, the pressure changed. But something that we really haven't looked at is if you increase the kinetic energy, and this goes back to the sort of the dynamic between kinetic energy and potential energy. So we know that if we increase the kinetic energy, we're going to get more vapor. We're going to get more molecules moving from a liquid to a gas. It's also true that if you lower the potential energy, you also get more molecules moving from a liquid to a gas. Because like I said, the balance is between KE and PE. And if KE is higher, we're going to see more molecules in the gas phase. Well, there's two ways to do that. You can either increase kinetic energy or you can decrease potential energy. Either one of those is going to get you more kinetic energy relative to potential and more molecules in going into the gas phase. The way that the chemists would say it is that the weaker these intermolecular forces, and remember, it's the intermolecular forces that are the potential source of potential energy, the higher the vapor pressure. So we don't say that we have we're talking about vapor pressure. So because we can't really say how do we express how many molecules are in the gas phase. You can't really say that the volume is increased or whatever. You just have to say that in a certain volume, the pressure has gone up. So we keep the volume static and then measure the amount of increased gas by the pressure, because it's really easy to measure pressure. So, and we've also talked about boiling point already, so I won't spend too much time on this, but boiling point of a substance is when its vapor pressure gets to the atmospheric pressure. That makes sense, I think. And so as the pressure on a liquid increases, if I put more pressure on a liquid, the boiling point has to go up because now the vapor pressure has to increase, has to go above 1 atmosphere. That's why a pressure cooker works. So if I put more pressure if I put a pressure of 10 atmospheres inside a pressure cooker, that water now has to get to the temperature where its vapor pressure is 10 atmospheres, not 1, in order for it to completely turn into a gas. And so that water is really hot. It's much hotter than boiling water at room in an open pot at 1 atmosphere. Why? Because it can't turn to a gas until it's gotten to that much, much, much higher pressure. And that's why it cooks so much faster, because the temperature is so much higher, even though it's still water, but it's water that's at a much higher temperature than it would be on the stove in an open pot. So here's that picture I was telling you about. I just wanted to include this because it's so pretty. So this is what iodine looks like. So this basically is, so you just got a test tube here. Like, duh, I know what a test tube looks like. So here's test tube with solid, iodine solid at the bottom, or iodine gas, basically. Iodine solid on the bottom, you heat it, and then you have iodine gas here. And then basically this is just called just have like another smaller test tube with some ice in it. And you can see you get these really beautiful, really dark violet crystals where it turns back into a solid. So that's called sublimation. And so iodine, although you might say to yourself, maybe you're saying to yourself right now, I've bought iodine at the drugstore. It's in a liquid. What is it? Has anyone seen iodine in the drugstore? Or how old? In the drugstore, back in the day. I don't know if iodine, I don't think people use iodine as an antibacterial anymore, but they used to. Anyone know what it is? That liquid you were getting?
Yeah, it's betadine, right?
Yeah, betadine, exactly. Yeah, so but it's a liquid. What gives? What do you think that is? It's not pure iodine, right? Do you know what it is? It's a solution. It's a solution of iodine solid dissolved in alcohol, because iodine is fairly nonpolar. And we'll see from this chapter, nonpolar things tend to become gases pretty easily. We sort of talked about that when we talked about during the gas laws. Gases are nonpolar at low temperature. CO2, H2, N2, O2, Cl2. They're all gases at low temperature. But if you, as we're learning now, you increase the temperature on anything, you can get it into the gas phase. Like water, for instance. Water is really hella polar, but you can turn it into a gas if you add enough heat. So yeah, iodine isn't a liquid, but it is soluble in relatively nonpolar solvents. And we'll be talking a lot about polar and nonpolar in this particular chapter as well, because that's a big part of this. So vapor pressure, we could actually measure how much intermolecular forces there are between molecules just by looking at the vapor pressure and the boiling point. So here's 3 liquids, and we've got ourselves water, and we've got ethanol, and we've got ether. Diethyl ether looks like this. Let me draw it out for you. So it's CH3, CH2O, CH2, CH3. So it's mostly a hydrocarbon with an oxygen in the middle. So it's fairly nonpolar, but it is somewhat polar because it has that oxygen in the middle. What shape would this be around the central oxygen? I'll ask. Is this going to be a linear molecule? Right around that central oxygen, what's the shape going to be? How many-
Linear or bent?
Very good. Yeah, it's going to be bent. Good job. How did you figure that out?
Because oxygen will have the two lone pairs of electrons that will repel.
So proud. Yes, yes. You learned that. That's awesome. Yeah, it's going to be bent. And it's because of its shape that keeps it from being nonpolar. If it was linear like this, it would be symmetrical. It would be completely symmetrical. It would be nonpolar, and its boiling point would be much, much less, because nonpolar things don't interact with each other as much as polar things do. And we'll find out what sort of interactions those are. But yeah, the intermolecular interactions or intermolecular forces between nonpolar molecules are much weaker than they are for polar molecules. And so I'm so proud. Yeah, so it's the shape. It's actually the shape of that keeps it from being nonpolar. And so it's not as polar, as you can see, as ethanol or water. So water looks like this. So I think we all know what water looks like at this point. And basically ethanol looks like half of an ether molecule. Ethanol looks like this. So instead of having the oxygen in the middle, it has it at the end. And so since we have oxygen at the end, we have a nonpolar side, which is the hydrocarbon side, and we have a polar side with the oxygen on it. So it is a lot more polar than the diethyl ether, which basically has two nonpolar ends and is polar in the middle. And so you can see the difference. We can actually measure how polar something is and how much intermolecular forces are holding those molecules together just by looking at their boiling point. So you see water, this is its partial pressure, and it goes up and up and up and up and up until we hit 1 atmosphere. So there's 1 atmosphere, and it hits 1 atmosphere at 100. Well, we knew that. Ethanol boils slightly less. It boils about 22 degrees lower temperature. And that's how we can distill booze. We can separate them, because when we boil a solution of water and ethanol together, the ethanol boils first. And basically, just like we saw when something boils, the phase is changing. Does the temperature change? So the ethanol is boiling off. Is the temperature of my mixture going to change? I've got a mixture of ethanol and water. It gets to 78.5 degrees, and then the ethanol starts to boil and turn into a gas. Does the temperature of my mixture of ethanol and water change at that point?
No.
No, it doesn't. It stays around 78, 79 degrees until most of the ethanol is gone. Ethanol is actually unique in that you can't boil it off completely. It forms something called an azeotrope, which is like a little beyond this class. But basically, you can't get it to more than 95% pure by boiling it. Once it gets to 95%, it forms this weird interaction with water, and you can't get rid of the rest of the water. So if you see anything that has 100% ethanol, don't drink it, because it's going to be incredibly poisonous. So anyway, moving on. So the ethanol has less polar interactions than water, but still polar interactions, because the boiling point is only changed by about 22 degrees. But let's look at ether. The boiling point of ether is like half, less than half of what ethanol is. Why? Because it has two nonpolar sides. and a polar in the middle. And so that leads to much harder interactions. Those polar interactions that we're going to be talking about are much more difficult, basically, when you're blocked by having two polar edges. So any questions about this? We're going to be talking a lot about polar and non-polar coming up, and I sort of want to make it clear what we're talking about, because we talked about dipoles infinitum, and this is why we were talking about dipoles. This is the real world changes that take place when molecules have dipoles and when molecules don't. Any questions on polar and non-polar? What I mean by that? What does polar mean to you? If I said a molecule is polar, what does that mean? Come on, you guys have been crushing the questions tonight. Don't let me down now.
There's an uneven distribution of electrons.
Mm-hmm. And where does the term polar come from? Why do we call it polar? There's a reason why we use that.
Is it because of the dipole?
Yes, because it has a molecular dipole. That's where the term comes from. So if a molecule has a substantial molecular dipole, we call it polar. And if it don't, we call it nonpolar. And so what we're going to be learning about is the difference in interactions between those two. So let's just do like one more, and we'll call it a night. So intermolecular forces arise from attractions between different molecules, okay, not within. So there's going to be attractions between them. And the attractions we're going to be talking about is like having partial charges. So two things with partial charges, like water. So we see that water with its slightly negative side and slightly positive side are going to interact with each other because, you know, you have partial charges there. And even partial charges want to get together, you know, have a little partial charge action. So the other interactions we're going to see are between ions and partial charges and ions and molecules. And they're all going to be slightly different. Now, these are relatively weak compared to, you know, single, double, triple bonds. We're talking about, you know, sometimes hundreds of kilojoules of energy keeping these things together. These are much less strong than that because they involve much smaller charges and they're much farther apart. When you have two atoms that are bonded to each other, they're really close to each other. Whereas when you have two molecules that are sort of interacting with each other, they're much farther apart, like 5, 10, 15 times further apart. And so any interaction that's that much further apart is going to be a lot weaker, okay? Oh, yep. And I think I'm going to leave it there. We'll pick up on this tomorrow. We'll talk about the different bonding forces. And the dogs are going insane. So, any questions about this or anything else before we wrap it up? Okay. Well, have fun at your lab tonight. It works really well. I like this particular one. It works like it should, and you won't have a problem. Macs, PCs, things running, you know, Linux boxes, whatever. It should be fine. And so I'll make a decision about the lab exam and get back to you about that. Get back to you about that, and then remember we've got the lecture exam dose on Friday. Okay.
Okay.
All right. Stay well, everybody.
Thank you.
All right. Thank you, guys. We'll talk to you soon.